Now let's talk about physical and logical cache organization. With regard to physical organization, a cache is centralized if its banks are adjacent on the chip, so if it's all in one place. Now Solihin uses the word united, but his book is the only place I've ever seen that term used. Everywhere else I've seen it as centralized. What are some advantages of a centralized structure? Well, the first is uniform access time because you're always going to the same place. The second is that the interconnect between the cache and the next level is simplified because it can be in one place. You don't need to run wires around the whole chip to access all of the lines of the cache or all of the banks of the cache. A centralized cache usually uses a crossbar. A cache is distributed, on the other hand, if its banks are scattered around the chip. Usually, each L1 has a portion of the L2 placed near it. So you have the L1 in conjunction with a processor and then a portion of the L2. And then you have your interconnection on the other end of that. And this would be in a multi-core architecture where it's feasible to distribute caches like this. In a different kind of an architecture, SMP, the different processors are probably on different chips, and then you have other issues. Well, what are some advantages of a distributed structure? There are actually two kinds of advantages. One is with regard to replication, and in that case, a single tile, which contains a core, an L1 cache or L1 caches because maybe the cache is split, in one bank of the L2, you can design and stamp that as many times as you need. So it's more scalable. It's easier to verify because all of the components are the same, and easier to use in the next generation. By golly, those are the same advantages that multi-cores have in general. And in layout, the advantage is this. It's more feasible for a many-core processor where wire length and thermal considerations, you don't want to heat one part of the chip up a lot more than other parts of the chip, prevent a cache from being centralized. So distributed works out well for many processors. There's a trade-off between centralized and distributed. A large cache is uniformly slow, especially if it needs to handle coherence. You know, a lot of things need to happen when lines are accessed or replaced. A distributed cache, on the other hand, requires a lot of interconnections, and routing latency is high if the cache is in too many places. In other words, if you have part of the L2 at the other end of the chip, it's going to take you a longer access time to get there than to the portion of the L2 that you have. And that may, depending upon how blocks are placed when purged from the L1, that may run up your average access time significantly. So a compromise is to have an L2 cache that's distributed, but not as distributed as the L1 caches. You see that you've got the cores in conjunction with the L1, and a few of them are all around a particular part of the L2 cache. So the L2 cache is in fact distributed to 4 places here, but there are 16 processors, so it's not as distributed as it was in the previous diagram. Now let's go on to logical cache organization. Regardless of whether a cache is centralized or distributed, there are several options in mapping addresses to lines. First of all, processors can be limited to using the portion of the cache, the tiles closest to them. And in that case, if there are blocks elsewhere, in other words, other processors can't use your cache, but if there are blocks elsewhere that are the same as your block, same address as your block, then you need to keep them coherent by a coherence protocol. Another approach is to have all of the processors, all of the cores, be able to access any part of the cache. So then the address of a block completely determines what tile it's found in, and in that case a particular processor might have to go across the chip to get to portions of the cache. But it's possible to allow more freedom in where to place the block. We just talked about a case in which the address of the block completely determined where it is. But it's also possible to have a cache or to have a block be placeable in two different tiles. And in that case, you put one of those tiles close to the processor and make the other one far away. The last option is that a block can be allowed to map to any tile, which means you have full associativity with regard to tiles. And well, that's got downsides and upsides just like fully associative caches. The upside is that blocks can always be placed close to the processor that's using them. But the downside is that it's harder to find a block, just like it's harder to find a block in a fully associative cache. You need to check more tiles to find a block, and there are formulas for that. We can work it out. We might have a homework question like this, but checking more tiles uses more power and increases network traffic. Another organization is Partition Shared Cache. And I've got 3 questions for you. Can you tell how many tiles each block can map to? Can you tell how many lines each block can map to? And how does coherence play a role?